My name is Cervenjak. I'm a PhD student here at the University of Melbourne. And actually, I submitted my thesis for examination last month. So currently, I'm just sort of waiting. Thanks. Just waiting for that, waiting for the reviews back. And this work on a radius-sensitive approximation algorithm for connected submodular maximization, that will be it is the last chapter of my thesis. Done in collaboration with my supervisors, Junhao, William, and Tony, and also with my collaborator Nanori Kakamura from Japan. And I actually had the privilege of visiting him in Japan last year from between May and June. Okay, so I'm just making sure this works. Ooh. Sorry, the clicker is not.
It was working before.
Yeah, I don't
That's
know.
what you tested.
Okay, I might just have to press the spacebar. Okay, I think it was the computer, I think. Okay, so the overview of the talk is we're going to introduce the topic and some of the concepts. We're going to look briefly at some of the previous work and motivate our research a little bit. Then we'll review the actual results that we obtain in our work. We'll go over the main ideas that we use to obtain the results, and then we'll just have some quick conclusions. Okay, so first we just introduce the problem. I'll just firstly say that for some graph, a mathematical graph, we define the size of that graph to be the number of edges. So we're going to just use that notation throughout the presentation. And the main problem we'll be looking at is connected submodular maximization. So here we're given a graph with vertex set V and edge set E, and we're given this certain function that's non-negative, monotone, and submodular. So I'll define what that is in the next slide. And it's defined on the vertices of G. And we're also given this integer k, which is going to be a size constraint. And the actual problem or the goal is to select a tree graph or a tree that's a subset, subgraph of the input, such that its size is at most k and whose vertices maximize the function. But we often just abuse notation and we just write the function applied to the actual graph itself. And then we also define a rooted variant. So this is not really studied as much, but it's just there as a subproblem that we use throughout our algorithms. So it's defined exactly the same, except we now specify a root vertex called V. And we just have this extra constraint on the graph that it has to contain that root vertex, while again maximizing the submodular function. And we define T star to be the optimal tree or the optimal solution, and OPT is the value of this tree. And as I mentioned, we also extend our results to directed graph, but I'm not going to really worry about that in this presentation because there's not really any difference between our algorithms in that case and in the undirected case. But just to give a quick example of this of an instance of this problem. So this is sort of a real life application of this problem where you want to find a connected network of UAVs so that they form a communication network, and you want to maximize their coverage or possibly their throughput, or rather maximize the number of users that are covered. So the function actually denotes the coverage of those UAVs. The constraint, again, is that they're connected and their size is at most 3 in this case. And the optimal coverage I've shown here in this solution is 12. Okay, so what actually is a submodular function? So it's basically any kind of set function that assigns values to subsets so that each element or vertex in this case exhibits this diminishing marginal gains property. So what that means is that if we fix a vertex X, and we consider its marginal gain or its added benefit to some set S, then it's not increasing if we enlarge the set. That's the diminishing marginal gains property. And as is quite standard, we assume it's also non-negative and monotone, so it increases or is might be a typo there. Sorry. Yeah, but it doesn't decrease when you enlarge the set S. And also we assume that we have to access the function via a value oracle, and that each query to the value oracle takes constant time. So even though we look at this problem more theoretically, there are a lot of interesting applications of this problem. So there's the UAV networks, as I mentioned before. There's deploying wireless mesh networks, so Wi-Fi networks. Deploying wireless sensor networks to maximize their coverage or informativeness. Also power charger networks, which can be used to wirelessly charge devices, including sensors. And there's also these other these more different applications, such as detecting gene mutations that best explain the presence of cancer. So the idea is that each mutation is associated with a set of patients that have that, or cancer patients that have that mutation. And then we want to select a connected network of mutations that covers the most patients that have that mutation. And we require the connectivity in this case because it's generally believed that the cancer arises from an interaction or a pathway of mutations. And then also there's this other application relating to identifying connected geographic regions that are more susceptible to an epidemic outbreak or like a disease outbreak. So the idea is that you want to select regions that are connected because it's better for public health interventions, or it makes it more effective. Okay, so now we'll introduce the kind of algorithms we'll consider. So you have to consider approximation algorithms because generally submodular maximization problems are NP hard. And in fact, there's a huge literature on approximation algorithms for these kind of problems. So just to define this, so an approximation algorithm, it outputs, let's say, an alpha approximation, where alpha is called the approximation factor. And it means that the value of the solution is at least, or is within alpha factor of the optimal solution. And also, we'll need this other kind of approximation algorithm called a bi-criteria approximation. So that means the solution is an approximation with respect to the optimal value and also the actual constraint. So this means, again, the value of S is at least alpha times the optimal value, and the size of the solution is at most this beta factor times the constraint, where we call beta the violation factor. So just to give an example of an approximation, so for the standard submodular maximization with the cardinality constraint, so in other words, there's no connectivity constraint, we can just run a standard greedy algorithm that just chooses or builds a solution by adding the element with best marginal gain in each iteration. And we get this 1 minus 1 over E approximation. So that's a very famous result. And in fact, it's well known that being this approximation for this standard, for the simple problem, is NP hard. So maybe you can see that this hardness of approximation also applies to our problem, because this is going to be a special case of our problem. Because if we take a complete graph, then it just reduces to the cardinality constraint problem. But actually, it seems, based on the past research, that this problem is a lot harder than that, because the best algorithm achieves a 1 over k to the epsilon approximation for a constant value epsilon here. Okay, so what we will do in our work is we'll parameterize the approximation guaranteed by this parameter called the optimal tree radius. So I'll just introduce what that is. So we first define V to be the center of the optimal tree in an instance of a connected submodular maximization. Or in the rooted case, if you want to solve that problem, it's just the root vertex. And the center is defined to be the vertex that minimizes its distance to the furthest vertex in this T star. So hopefully you can see in the picture that this is sort of the most central vertex, right? So it only has a distance of 3 to the furthest vertex. And then we let R just be the radius, so it's this actual distance that's minimized. But in the rooted problem, it's the height. So there's not really much distinction between the unrooted and rooted problem. It's just that the bound on R is a bit different. So in the unrooted problem, R is going to be at most K on 2, whereas in the rooted problem, it's at most K. And so sort of the motivation or what makes this radius interesting is that it would be useful in small world networks. So these sort of, usually they're associated with social networks, but they also appear in other networks like the gene interaction networks. This is defined as any network where the average distance between a pair of vertices is proportional to the log of the number of vertices. And also, as we'll show, a smaller value of R makes the vertices more reachable from the center. So it actually makes the problem easier, as I'll show in this example. So if the radius is, the optimal tree radius is equal to 1, we can actually achieve the same approximation guarantee as for the cardinality constraint problem. Because all we have to do is just guess this, this center here. We just initialize our solution with this center, and then we just add the neighbors using a greedy algorithm. Okay, because, yeah, all those neighbors are going to be automatically connected to our solution. Okay, so let's look at some of the previous work on our problem. So mainly polynomial time algorithms have been studied for this. So this was first introduced by Kuo, who achieved a roughly 1/√of k approximation with this constant factor of 0.126. And then some of the later works just basically improved on this constant factor. So Chu gave improved this by a factor of roughly 5, and then Lee basically they allowed for a parameter s in the approximation where s can be any sort of value, but it has to be a constant in order for it to be a polynomial time algorithm. And actually, there are some more sophisticated results that are not sort of explicitly written in the literature, but I think they're still worth mentioning. So a result by Im implies a polylog approximation depending on the number of vertices. But it's not as useful because it doesn't extend to directed graphs. It requires embedding the input graph into a tree. So that doesn't work. That technique doesn't work for directed graphs. And then also this result by Kalinescu and Zelikovsky, they gave a recursive greedy algorithm for this related problem of polymatroid directed Steiner tree. So don't worry too much about it, but it's just sort of it's like a variant of Steiner tree where you're trying to cover a submodular function or an integer valued submodular function. But the point is that the algorithm can be shown to imply this approximation with 1/k to the epsilon. And now, as for these radius-sensitive approximation algorithms, so algorithms where the approximation depends on this radius parameter, only 2 previous works have looked at it. So Bandin, they gave a 0.387/r approximation algorithm in polynomial time. And then Hochbaum and Rao, they improved this by a constant factor again. So you might notice that these approximations, although for very small r, they're definitely better than the previous ones. The dependence on r is not the same, so it's not like a 1/square root of r. And in fact, it degrades to the trivial 1/k approximation in the worst case. So this was sort of a gap for us. It seemed like when r is equal to 1, the problem is easy, but then all of a sudden when r is proportional to k, the problem, or rather the algorithm behaves quite poorly. So this was sort of like the main motivation for our work to see if we can come up with a better approximation with respect to R. So we'll just look at this algorithm briefly and sort of explain why it gives that 1/r approximation. So the basic idea of the algorithm is to guess the optimal center, and then we construct a BFS tree rooted at that center, so that we sort of obtain all the shortest paths from V to all the other vertices. And then we just guess the radius of the optimal tree. We initialize our solution with V, and then while it's still possible to add edges into our solution, we find some vertex W at depth at most R in the BFS tree, such that the path from the center to W has the best marginal gain to the solution, and we just add that path to the solution. So this seems like a fairly good idea. So if you run the algorithm, it'll look like something like this. You might pick these vertices and then you add these corresponding paths. But the problem is that actually it's very hard to find the best path because there could be exponentially many of them from B to one of these vertices W. So what can happen is that you end up adding these paths that contain only one valuable vertex, but all the other ones are basically useless. They're basically low value vertices. And so you end up spending R edges just to connect one vertex. So it's actually quite wasteful in terms of the number of edges it uses. And that's basically why you get a 1/r approximation, because you fill up the size constraint quickly without getting too much value. Okay, so now let's look at our results. So here's our main theorem. So we first consider the unrooted connected submodular maximization problem. So we have our instance involving the graph, the function, and the constraint K. And then what we show is that there exists an algorithm that returns a epsilon cubed over R, the epsilon approximation, and it runs in basically polynomial time for any fixed epsilon. And then we also give a similar result, but for the rooted version, we give a bi-criteria approximation. So if we have an instance G, function f, k, and a root v, then we show that there exists a bi-criteria approximation algorithm, which has essentially the same approximation, except we have a delta here, and it violates the constraint by this factor of 1 plus delta, and it has the same running time as before. And hopefully you can see that these approximations, they don't degrade any worse, or rather they achieve the best known approximation depending on K as well. And just quickly to just sort of compare again, so I already showed these results in the previous slide, but basically we beat those results that are sort of explicitly given in the literature whenever epsilon is at most 1/2. So for the radius sensitive algorithms, we beat it when epsilon is less than 1. And then for those other algorithms that give 1/√K approximations, like I said, we beat them whenever epsilon is less than 1/2. So we can choose epsilon to be 1/3 or 1/4, it doesn't really matter. And there's the result for the rooted connected submodular maximization problem. There are also algorithms on a more general budgeted version of our problem, and they also have like a similar budget violation, but they also have a square root of K in their approximation. That's not really that important. Okay, so what are the actual main ideas that we use in our framework? So first of all, we have to introduce this quick lemma. So it's not really, we don't derive this, we just get this from the older paper. And we use it quite often throughout our framework. So basically, the lemma allows us to decompose or partition an arbitrary tree into smaller subtrees. So just quickly, we let this parameter s. We just choose some parameter s in the lemma, and we assume the tree has size at least s. Then it's possible to partition it into these delta edge disjoint subtrees, T1 up to T delta. And each of these subtrees, has size between 1 and roughly 2 times s. And the number of subtrees is at most the size of the tree divided by s. And it's not really important for us, but basically the idea of achieving this partitioning is that you split away, or you sort of identify subtrees of T that have size within this range S to 2S. So it's always possible to identify such a subtree by considering, or by sort of classifying the hanging subtrees into light or medium subtrees or heavy subtrees. But I won't really go into the detail about that. But then, anyway, and then you keep splitting away these subtrees, and then eventually you just stop once the size of your remaining tree is less than s, and then you just assign it to be the last subtree. So just quickly, as an example of applying this lemma, if s is equal to 2 and the size of t is 16, then plugging those numbers in, we just get that the size of each subtree is at most 4, and there are at most 8 subtrees. Okay, so now let's actually move on to our algorithms. So we'll first introduce the two main algorithms that we use and state their guarantees. And then in the next slide, I'll sort of explain how everything fits together. But basically, our framework uses these two algorithms, first being greedy radius, which is the sort of the one that we actually introduce, or the novel algorithm. And we also devised this algorithm called the RecReProx, which is also a recursive greedy algorithm, and it's quite similar in structure to the previous recursive greedy algorithms. Yeah, and actually RecReProx is a bit more complicated, so I'm not actually going to go over that in this presentation, but it basically uses a kind of a similar structure to some existing algorithm. So in theorem 3, this states the guarantees of greedy radius, and we state them as applying to the rooted problem, and then later I'll show how to get the solution for the unrooted problem. So greedy radius takes this instance of the rooted connected submodular maximization problem, and it also takes as input this subroutine algorithm, which we just say achieves this by criteria approximation depending on k. And so I've introduced these terms alpha of k and beta of k, and alpha of k is just the approximation term in the by criteria approximation, and beta is the violation factor. And then also gamma of n of k is just the running time of the subroutine. And so the point, or the interesting thing about this greedy radius is that it takes this this subroutine whose approximation depends on k and returns basically the same approximation depending on r. So you can see there's just this constant of 1/2 and 4 here, but basically the approximation now depends on r instead of k. And also the running time just goes up to k times n times the running time of the subroutine. And then for RecReProx, we have that theorem 4 states that it outputs a by criteria epsilon, comma 1 over epsilon squared times k to the epsilon approximation. And it has this running time here, which is polynomial for any constant epsilon. So basically the idea of our framework, as I'll explain, is that we're going to plug in RecReProx into alg, and we'll sort of spit out the guarantees that we want in terms of R rather than K. So here's the basic framework. We have this greedy radius algorithm, like I mentioned. It takes as input an instance of G, F, K, and V. So it can either represent an instance of the unrooted version, and we just treat V as the center of the optimal solution, or as I mentioned, it just takes an instance of the rooted version. And then we also just say it takes as input a guess of the radius. So we won't really worry about guessing it inside the actual algorithm. And as before, it takes as input this bi-criteria approximation subroutine alg. And as I said in the theorem statement, it outputs this bi-criteria approximation depending on R. So it sort of converts, like I said, it converts the bi-criteria approximation of alg into one in terms of R. And then finally, if you want to get a solution for the unrooted problem, or rather a feasible solution, we just do this post-processing procedure, which involves the tree partitioning lemma I mentioned earlier. And then you can also reduce the size violation to 1 plus delta, using using a similar tree partitioning. Yeah, so hopefully you can see by plugging in rec_approx as this subroutine, we can get the actual guarantee that we stated earlier in theorems 1 and 2. So basically all that's happening is I'm substituting epsilon as alpha of k and this term as beta of k, but then I just change k to r. And so that gives us well, from here it gives us this term. And then you just do the similar thing for the rooted problem. So first we'll look at greedy radius, and just to give you some intuition about why it works, sort of the idea of greedy radius is to, instead of approximate valuable vertices in the optimal solution, we try to approximate valuable subtrees where these subtrees have size r. And then we also have to add these connecting paths of length r from this root vertex v. But the idea is that, well, we add, or we approximate more vertices for each path. So we actually get more value for each path that we add. And yeah, each valuable subtree is going to come from the tree partitioning of the optimal tree. But the thing is that approximating or finding these valuable subtrees, that's just sort of reducing the problem to a smaller instance of the problem. So we have to call this subroutine to actually find the approximation for us. And so basically, what happens is that for each subtree, we get this an alpha of r approximation, and we spend 2 times beta r times r edges, because we spend beta of r times r to approximate the subtree itself, and then we add r many edges to connect it. We just sort of simplified it to beta stuff. And then we'll show a bit later that we have to use 4 beta of r times k edges overall to approximate the entire subtree. Excuse me, the entire optimal solution. So this, yeah, so basically the blue sort of graph is the optimal solution, and this black graph is going to be the solution that we use to approximate T star. And just to give a bit more detail, so again, we assume T star is partitioned into this many edge disjoint subtrees, so T star 1 up to T star delta, each of size at most radius r. And then to actually run the algorithm, we initialize the solution with v, and then over iterations from 1 to delta, we we let T star sub Ji be the subtree in the partition that has the best marginal gain to the current solution. And so the idea of this algorithm is that in each iteration, we want to actually guess one of the vertices in this best subtree. And then maybe you can see that, well, we can actually just call L to approximate that subtree because we can just consider the instance of our rooted connected submodular maximization problem, where the root is one of these vertices, Wi, and the size constraint is R. So the size constraint is just the same as the size of the subtrees that we're considering. And then we also just pass the marginal gain function with respect to our current solution. So hopefully you can see that this T star Ji is going to be a feasible solution to this reduced instance, and therefore any solution that we get back from ALG is going to be an approximation with respect to this subtree. And then once we get back that solution, we just connect it to our current solution S. So the algorithm sort of just progresses like this. So we just assume that each of these subtrees of T star, they just have the best marginal gain in order from left to right. It might, guess this vertex and then approximate it. Might guess this vertex and then return an approximate solution, and so on. And just to give you a rough idea of the analysis, I won't go into too much detail, but basically, to analyze this algorithm, we analyze first the actual approximation term half alpha times R. We just use a standard greedy analysis. So we can actually just use the fact that each of these subtrees are sort of these elements, or they're sort of they can be the greedy elements of the optimal solution. But of course, when we can't find those elements or these subtrees exactly, so we just have to call that subroutine in order to approximate them. So we just sort of plug in this alpha of R term into a standard greedy analysis, and we get back a half alpha of R approximation. And then to prove the violation factor, so it's kind of fairly straightforward arithmetic. We first observe that we use beta of R times R edges to approximate one of the subtrees. And we use another R edges to connect it to the root. And then we add delta many of these subtrees to our solution. So just multiplying those and simplifying it gives you the size of our solution, S. So like I mentioned earlier, we just simplify this as 2 beta R times R. We substitute our value for delta and then just cancel them out, and we get that the final size of our solution is 4 beta R times K. So that means this violates the size constraint by 4 beta R. Okay, so that's basically how 3D radius works. And then now let's move on to these post-processing procedures. They're not too difficult. It's just some standard tree partitioning that we apply to the actual output solution, S. So once again, greedy radius outputs this solution S, which is a bicriteria, or roughly bicriteria alpha of R and beta of R approximation. And then to actually get the final solution for our, or let's say an instance of connected submodular maximization, excuse me, we partition that solution S into delta at most 8 times beta of R edge disjoint subtree. So we just use that partitioning lemma that I mentioned earlier. And each of the subtrees has size at most K. Then all we have to do is just pick the one that maximizes the submodular function. So hopefully you can see it has size at most K, so it's definitely feasible. And then again, we just use a standard argument. We use the fact that this subtree S hat is going to have value at least the average value of the subtrees of S. So therefore, it has to have value at least 1 over delta of the value of our original solution S. So yeah, basically from there, I'm just plugging in the value. So delta is h times beta of r, and then I plug in the fact that the value of S is at least alpha of r over 2 times the optimal solution value. It simplifies to this approximation. Yeah, so that's that might be one of the subtrees that we get. And then finally, to get this bi-criteria approximation for the rooted problem, where we reduce the violation factor, we do something a bit similar, but we just have to add a connecting path. Or actually, before we actually run this procedure, we have to assume that the graph is pruned so that all vertices from the root have distance at most k. So this will be because the connecting path, we have to ensure that the connecting path has distance at most k. Then we partition the output tree similar to before, but now we just have this extra factor of delta here in the denominator. So that means that all of our subtrees that have size at most delta times k rather than size k. And then we pick, as before, we pick the subtree that maximizes the submodular function, and we let wj star be its root. So it might be this subtree, for example. Then now what we actually return is s hat equal to this subtree combined with a v to wj star connecting path. So similar to before, we can prove that s hat has the appropriate value. And we just point out that the value of s hat has to be at least the value of sj star because f is monotone. And then from there, it's at least the average value of the subtree. So again, it's 1 over delta times the value of f of s, the value of s. And we just plug in the value of delta, the value of f of s. And again, we simplify this to our approximation, but we have this delta factor here. And then finally, this is quite straightforward. The actual size of our solution is going to be the size of our subtree plus the size of the connecting path. So it's just going to be delta k plus k. And again, because we pruned the graph before running our algorithms, the connecting path has size at most k. So we get a 1 plus delta violation factor. Yeah, so that's basically all I'll explain. So just to summarize the framework, the main idea was to use this greedy radius algorithm that we proposed to take some instance of our connected submodular maximization problem or the rooted variant, and in particular take some subroutine that is a bi-criteria approximation for this problem, and then it converts that approximation to 1 in terms of r rather than in terms of k. And then we can just apply these trimming procedures to get either a feasible solution for the unrooted problem or a solution for the rooted problem, but with a 1 plus delta violation factor. Okay, so just to wrap up, so we studied this network design problem, the connected submodular maximization problem and its rooted variant. And in particular, we studied this parameter r that we can achieve basically beyond worst case approximation, especially for small value of r. And we gave this epsilon cubed over r to the epsilon approximation for the unrooted problem, and this bi-criteria approximation with the 1 plus delta violation factor for the rooted problem. And again, both of these algorithms run polynomial time when epsilon is constant. So I think there are some interesting ways to extend this research. So it might be interesting to look at other parameters. So there are some other parameters in the literature that have been studied, but maybe not fully or thoroughly. So there's a parameter called h-hop independence, and there's also the doubling dimension of a metric graph, so it might be interesting to see whether we can show similar improvements, or even consider some other parameter entirely for the graph. And then there are also some open problems related to our computational problems. So for the rooted problem, we don't actually know if we can achieve a non-trivial approximation without violating the size constraint. So in other words, without having to use a by criteria approximate solution. And also, as I mentioned earlier, we have this 1 minus 1 over E approximation harness for the connected submodular maximization problem. But it really looks like the problem is actually much harder than what this result suggests. I don't think there's a constant, I highly doubt there's a constant approximation for this problem. So it'll be interesting to see if we can prove something like even a polylog approximation harness for connected submodular maximization. Okay, so that's all I have to say, and